Coming to the next type of solution, which is known as non-ideal solutions. As told earlier, non-ideal solutions are those which do not obey Raoult's law. So here you can just change this definition as non-ideal solution. Non-ideal solutions are those which do not obey Raoult's law. That means this equation and this equation is never followed by the non-ideal cases. So then we can represent it as PA not equal to P0AXA, PB not equal to P0BXB, and where delta H of mixing is never equal to 0, delta V of mixing is never equal to 0. In such a condition, we say that V solute, that is volume of the solute plus volume of the solvent, is never equal to volume of the solution, and this happens because the solvent interactions are not equal to solute interactions, which are not equal to solvent solute interactions. So such cases we say that it is non-ideal solutions. We have two types of non-ideal solutions. We'll be seeing it one by one. Characteristics of non-ideal solutions. We'll be discussing about how the non-ideal solutions behave and what are the different types of non-ideal solutions. We find that there are two types of non-ideal solutions. One which show positive deviation from Raoult's law, and the other one which shows negative deviation from Raoult's law. First, we'll be seeing the characteristics of non-ideal solutions which show positive deviation from Raoult's law. In this case, you find that delta H of mixing is always more than that of 0. Delta V of mixing is also more than 0. And you find that P0AXA and P0BXB is not following the Raoult's law. That is, PA is greater than P0AXA, PB is greater than P0BXB. These conditions occur when A-B interactions, that is solute-solvent interactions, become weaker than that of solute-solute interactions and solvent-solvent interactions. That is, solute-solvent interactions must be weaker than solvent-solvent or solute-solute interactions. This happens in the case of ethanol and acetone mixture. Ethanol has the formula C2H5OH. When it is mixed with acetone with the formula CH3COCH3. As such, ethanol has the structure ROH. So, ROH will have hydrogen bonds in between. In this, you find that oxygen is carrying a slight negative charge, whereas hydrogen is positively charged. So that will be attracting the negatively charged oxygen of the next one. So then this will be in the hydrogen bonded condition. When we are adding acetone to it, you find that acetone will interrupt the hydrogen bonds, and so the molecule becomes free in nature. So, when the molecules are free entities, they can escape out faster as vapors. So, vapor phase will increase, vapor pressure will increase when there is weak interaction between the solute and the solvent. So, then you find that the solute solvent interactions are weaker compared to that of the solvent solvent or the solute solute interactions. With the result, what happens is the molecules become free in nature, it will change into vapor easily, vapor pressure increases. When the vapor pressure increases, the liquid starts boiling at a lower temperature. That means the boiling point of the solution becomes lesser. So when ethanol is mixed with acetone, the boiling point is found to decrease considerably, and this happens because of positive deviation from Raoult's law. Solutions which show positive deviation from Raoult's law is found to boil at a lower temperature, due to which you find that such type of solutions will boil at a minimum boiling point, and such solutions which are constantly boiling mixtures are known as minimum boiling point azeotropes. Minimum boiling point azeotropes are solutions which behave like a single compound and which cannot be separated by simple physical methods like fractional distillation. They behave like a compound, and it is very difficult to separate out the components from the mixture. For example, if you take ethanol water mixture, if the ethanol water mixture is composed of 95% ethanol, this composition, the solution behaves like a simple chemical compound, and the components of ethanol and water can never be separated under that composition, that is 95% ethanol and 5% alcohol. It is found to boil at a temperature lower than expected because it is a minimum boiling point azeotrope. The graph seen here shows the representation of an ideal solution. In the case of positive deviation, what are the conditions that we have learned? Delta H of mixing must be greater than 0. Delta V of mixing must be again greater than 0. PA must be greater than P0A XA. PB must be greater than P0B XB. And the last condition is AB interactions are weaker than AA or BB interactions. That is, solute-solvent interactions are weaker compared to that of solvent-solvent interactions or solute-solute interactions. So we will convert this graph into the non-ideal case. What did we learn here? The vapor pressure of A must be greater than that of P0A XA. So this is a graph representing that it is equal to P0A XA. So it should be more than that. That means there should be a positive heap on the graph. Coming to the second case that is B. PB must be greater than P0BXB. That is, this is PB equal to P0BXB. So there should be a leap in the curve. That means the graph should be more than that is expected from Raoult's law. So what will be the net effect? The net effect is that when we are adding the solute and the solvent in the solution, you find that if there is a positive deviation from Raoult's law, that will be considered as the solution which shows positive deviation from Raoult's law. So what are the main conditions here? Remember that it should be always having delta H of mixing greater than 0, delta V of mixing should be greater than 0, PA must be greater than P0AXA, PB must be greater than P0BXB, and the solute solvent interactions are always weaker than solvent solvent or solute solute interactions. Come to delta H of mixing greater than 0. Delta H of mixing greater than 0 means delta H of mixing should be positive. That is, the solution when A and B are mixed together, it should form a cooler solution, that is, it should absorb energy, or it is an endothermic reaction. We say that this is a solution which shows positive deviation from Raoult's law. Examples: examples for positive deviation from Raoult's law, that is ethanol, acetone mixture, acetone carbon disulfide mixture, ethanol water mixture, methanol water mixture, etc. Carbon tetrachloride methanol mixture, cyclohexane ethanol mixture. All these are examples of positive deviation from Raoult's law. We shall now just try briefing the solutions which show negative deviation from Raoult's law. The characteristics of solution showing negative deviation, we shall summarize it as delta H of mixing should be less than 0, delta V of mixing is less than 0, then PA must be less than P0AXA, PB must be less than P0BXB, and all this happens whenever AB interactions are more stronger than AA interactions or BB interactions. That is, solute-solvent interactions are stronger compared to solvent-solvent or solute-solute interactions. This is depicted in the graph as follows. We have just drawn the case of ideal solutions. We learned that PA is equal to P0AXA, PB is equal to P0BXB, and P total or the P ideal solution is the sum of PA and PB. Now coming to the solutions which show negative deviation. So accordingly, we have learned that the vapor pressure of the pure component is always lesser than that of P0AXA. That is, it will be always having a lesser value that is expected than from the Raoult's law. Same is the case with the solvent too. Solvent also shows less vapor pressure compared to the theoretical value as told by Raoult's law. Resultant solution also will have a vapor pressure lesser than those which are shown by Raoult's law. So then this represents the condition that is the negative deviation, and this happens when solute solvent interactions are more stronger. New bonds are formed between the solute and the solvent, resulting in stronger interaction between the solute and the solvent, which makes the escaping tendency of the molecules lesser. With the result, the vapor pressure of the solution will be lesser, and so it takes more time to boil, or boiling point of the solution keeps on increasing. So we find that solutions which are having negative deviation usually show a heap in the value of the boiling points, and such solutions which show maximum boiling point azeotropies. So at a particular composition, the binary mixture behaves like a chemical compound where we cannot separate the components by simple distillation or fractional distillation, and you find that such cases they usually show maximum boiling point azeotropies. Solutions which show negative deviation from Raoult's law always form maximum boiling point azeotropies. Examples are hydrochloric acid and water mixture, then nitric acid water mixture. All these are showing positive deviation from Raoult's law. On just checking the condition delta H of mixing less than 0, what do you understand by this? Here you find that energy is liberated when the components A and B are mixed together. That is, when the solute and the solvent interacts together, it releases a lot of energy. Such cases we say that it forms solutions which are having a maximum boiling point azeotrope. Hope it is clear. Thank you.